Hello students, welcome to class 11 physics class. Today we discuss another one new topic of this chapter, laws of motion, that is impulse. In last videos we discussed the first law, second law, third law of Newton's, the free body diagram and some numericals related to that. From first law we get the idea about linear momentum, the force and the inertia. And from second law we get the idea about the linear momentum and also the force. And third one is related to action and reaction. This is also related to force. Okay, different form of force. Today's topic, that is impulse. It is also one type of force. One type of force. Okay, not similar to the force, but one type of force. Different kinds of forces are there. Okay. So let's start with today's topic, that is impulse. What is impulse force or impulsive force? Impulse is a phenomena and the force which acting on it, that is called impulsive force. So impulsive force is a large force. It is not a simple force. It is a large force acting for a very short time to produce a finite change in momentum is called impulsive force. That means this is a one special type of force which magnitude is high, is larger, but it will act for a very short time on an object. And when it will act on an object, there will be a finite change in momentum. Momentum also change, but that change is finite. Suppose in for 1 second or for 0.5 second, it will apply a large amount of force and it will change its momentum change, finite change in momentum is there. Then that type of force is called impulsive force. Force exerted by a bat while hitting a ball. So that means when a ball throws through by the bowler, that ball will apply a large force on the bat, or we can say that action and reaction. But this is very short time, but large amount of force is acting on it, and due to that, when the bat will be exerted a force on the ball, the momentum of that ball will be changed finitely. So that kind of force are called impulsive force. So impulse, that total effect, that is when a large amount of force act on it for a short time and it will produce a finite change in momentum, that total procedure, total phenomena is called impulse, and that force, that large force is called impulsive force. Is called impulsive force, like a resistance and resistor. You know that in class 10 you studied resistance is a property of a resistor, and a resistor is a device. Resistor is a device, and the property of that resistor is called or characteristics is called resistance. Like that way, that large force which is acting on an object, that is called impulsive force, and due to the total process, whatever the change, whatever the effect after applying that impulsive force, that is called impulse. That is called impulse. So we can say that impulse equals to force into time duration, that is equals to total change in momentum. Impulse equals to force into time. Why time duration? Because it is act for a very short time. Force into time duration, due to that, what is the effect? Total change in momentum. So impulse, mathematically we can write impulse is the product of the force and the time for which it acts, and it is equal to the total change in momentum, and it is a vector quantity. You have to keep it in your mind. We know that force is a vector quantity, so it is also a vector quantity, and it is denoted by J vector. It is denoted by J vector, by J, not with a F. Normally the force will be denoted by capital F, but here the impulse will be denoted by J. And the direction of impulse, in which direction that this momentum will change, is the same as per the second law, in which direction the force will be applied. Same direction of the force. Clear? So we can conclude that this impulsive force or this impulse, it is a positive or negative. Negative means if it momentum change is the opposite direction of the applied force, and zero depending on the momentum of the body increases, decreases, or remains unchanged. Remains unchanged. If we apply sorry, not the opposite of the body, because its direction is same as that of the applied force. So when it will be positive, when its momentum will increases. If the large amount of force is applied on it and its momentum increases finitely, then we can say that this will be positive. If its momentum decreases when we apply a large amount of force for a very short time, then we can say that it will be negative. And zero if no change, if remains unchanged, that is called zero. I hope it is clear. Impulse. Now, so today here that from impulse we get another one idea about the linear momentum. So we can say that from impulse we get a relationship between a force and a linear momentum. Force and a linear momentum. So now today we discuss the laws of conservation of linear momentum. We know a little bit, we studied in class 9 about this linear momentum. So what is the law of linear momentum? Its statement is when no external force acts on a system of several interacting particles. So system means inside the system many particles are there, many bodies are there. Okay. So on that system, if no external forces act, then the total linear momentum of the system is conserved. The total linear momentum, suppose that system will consist with suppose 5 particles. Each particle have their own momentum. Suppose first particle have first momentum P1, because we know that momentum is denoted by P. P1, second particle P2, third particle P3, fourth particle P4, like P5. 5 particles are there, and they will constitute a system. So if no external force is applied on that system, then the total momentum of the system will be conserved. Then P1 plus P2 plus P3 plus P4 plus P5, that is equals to constant. Okay. And the total linear momentum is the vector sum of the linear momentum of all the particles of the system, because momentum is a vector quantity. So that addition P1 plus P2 plus P3, that is a vector sum of the momentum, and that is equals to the constant. So we can prove this also mathematically. Here we consider an isolated system. Isolated system means the system on which no external force acts. Isolated means no external force is acting on that system. So we consider an isolated system consists with n particles. In number, here I will consider the 5 particles in place of 5. We considered n particles. Suppose the n particles have the masses m1, m2, m3, like up to mn, and they will move inside the system with the velocities v1 plus v1, v2, v3 up to vn. So the total linear momentum of the system, that is equals to, we know that momentum means mass into velocity. So the total momentum of the system means sum of this all mass and product of mass and velocities. So we can write this one mathematically. P1 equals to m1 v1 plus m2 v2 plus m3 v3 plus up to mn vn. So as we know that m into v, that is a linear momentum P. So we can write P equals to m1 v1, that is equals to P1, like this way, P1 plus P2 plus P3 up to Pn. Now if we consider, if F is the external force acting on the system, Up to that, we consider no force is acting on it. So the total linear momentum will be this: P equals to P1 plus P2 plus P3 up to Pn. Now, if F is the external force acting on the system, then according to the Newton's second law, we know that when a force is acting on a system, on a body, it will be equal to the rate of change of linear momentum. So we can write F equals to dp by dt. So in that equation, we can write, because F is equals to 0, F is equals to 0, so dp by dt, that is equals to also be 0. As the derivative of the constant is 0, then if we write only P equals to constant, dp by dt equals to 0. So P equals to, because we cannot differentiate the 0. If we differentiate the 0, that will be a constant. So P equals to, we can write constant, and P equals to, we get P1 plus P2 plus P3 up to Pn. So we can also write P1 vector sum of P1 plus P2 plus P3 up to Pn, that is equals to constant. So this is nothing but that statement: when no external forces acts on a system of several interacting particles, the total linear momentum of the system is conserved. The total momentum is the vector sum of the linear momenta for all the particles of the system. So this is in the absence of external force, the total linear momentum is constant. This is nothing but the law of conservation of linear momentum. Law of conservation of linear momentum. Okay. Now we derive the law of conservation of momentum from Newton's third law, that is from second law. We can use that is second, because here F equals to dp by dt. This is nothing but the second law. So now we prove the linear momentum, conservation of linear momentum from third law of Newton's: action equals to minus of reaction. So here first we consider two bodies A and B having the masses m1 and m2 moving in the same direction along a straight line with the velocities u1 and u2, and here we consider the velocity of first particle or first object will be greater than the second, and after some time, after very short time, delta t, we consider here, they will collide each other. So after collision, their velocities will be v1 and v2. As per this equation, first one, before collision, they will move in a straight line in a same direction, A having the mass m1 and B having the mass m2, and the velocities are u1 and u2. After some time, they will collide each other. So during the collision, when A and B are contact to each other, so both the bodies will exert a force on each other, that is one FAB, force on A due to B, that is right side left side direction, and the force on B due to A, that is FBA in the right side direction. Now after this collision, when they will again move they will separate and again move in a straight line with a new velocities, that will be v1 and v2. So we can say that during collision, the second one diagram, second number, during collision, the force exerted on A by B, that means FAB, and the force exerted by A on B, that is FBA, and AB is the force exerted on A by B. Now according to the third law, these two forces will be equal but in a opposite direction, but not cancel each other. As we already discussed, these two, action and reaction, takes place in a different bodies. That's why these two are equal and opposite but not cancel each other. So we can write FAB equals to minus of FBA, and this is a vector. So from vector we can also know that when we studied the vector, that is F of AB, that is equals to minus of FBA. Now impulse of FAB, if we apply the concept about impulse of FAB, because that is a time duration, there will be delta t, very short time. After collision there will finite change in their momentum, they will acquire the velocities v1 and v2. So we can write impulse of fab, that is equals to fab into delta t, because impulse equals to force into time duration, that is equals to total change in momentum of a. Total change in momentum of a, that means m1 v1 minus m2 m1 u1. M1 v1, that is after collision, it's the momentum of body a, and m1 u1 is the before collision, the momentum of a. So the change in momentum, that is m1 v1 minus m2 m1 u1. Now similarly we can write f of ba, that is equals to fba into delta t, that is equals to, we can write m2 v2 minus m2 u2. But as we know that FAB equals to minus of FBA, and if we multiply delta T both side, FAB delta T, that is equals to minus of FBA delta T, and if we put these values, that momentum values M1 V1 minus M1 U1, that is equals to minus of M2 V2 minus M1 M2 U2, and if we simplify this one, we get M1 V1 plus M2 V2, that is equals to M1 U1 plus M2 U2. So M1 V1 plus M2 V2, that will be the total linear momentum after collision, because A and B consist a system. If we consider both as a system, so the total linear momentum for both the body due to the A and B, that will be m1 v1 plus m2 v2, and this is after the collision, and m1 u1 m2 u2, that is before the collision. So we can write total linear momentum after the collision, that is equals to total linear momentum before the collision. So if from here we can see that after collision and before collision, momentum will be equal to each other, so this proves the linear momentum will be conserved. Linear momentum will be conserved. Another one, from Newton's from this law of conservation of momentum, we can also prove Newton's third law of motion. The previous video we discussed, we proved the linear momentum, conservation of linear momentum from Newton's third law of motion. Now just opposite, from laws of conservation of law of conservation of momentum, we find out or we derive Newton's third law of motion. So here also we consider two bodies, m1 and m2, moving along a straight line and colliding against each other with the velocities after the velocities, and hence the momentum of the bodies undergo change. Let the delta P1 and delta P2 be the change in momentum produced in time delta T, because here we find out the Newton's third law. So here we consider the change in momentum delta P1 and delta P2. Now according to the law of conservation, the net change in linear momentum in the absence of external force will be 0. So we can write delta P1 plus delta P2, that is equals to 0, or delta P1 that is equals to minus of delta P2, or delta P2 equals to minus of delta P1. Now if we divided both sides by delta T, so delta P2 by delta T that is equals to minus of delta P1 by delta T. So this is nothing but we can say that rate of change of momentum of mass m second mass, that is equals to minus of rate of change of momentum of m1. So rate of change of momentum, that is nothing but the force on m2, that is equals to minus of force on m1. So force of m2 is a action and force on m1, that is a minus of reaction. So this proves the Newton's third law of motion. This proves Newton's third law of motion. I hope it is clear to everyone. Just here you consider in last, you consider the after collision the some velocities will be v1 v2, this one. Here you consider that the change in momenta, that will be p1 and p2, and with this help of this law we find out this one, differentiate both side, and because rate of change of momentum from the concept of impulse, that is equals to force into time. So force on m2, that is equals to minus of force of m1, that is nothing but action and reaction. So this proves the Newton's third law of motion. Next topic is apparent weight of a man in a lift. So if few, not the everyone, I hope few of them from class 11 science you use the lift, and at least one time you also use the lift. Okay, and did you feel this changes or not? I don't know, but I will fill this one. So, apparent weight of a man in a lift. Three diagrams are there. Three different cases are there. So, here we consider a man whose mass is m standing on a weighting machine placed in a lift. Inside a lift, you placed a weighting machine and you stand on that machine inside the lift. Now, the actual weight of the man is mg, that is due to the gravity, whatever the force acting on it, that is mg, that is its actual weight. It acts vertically downward through the center of gravity g of the man. We know this one. As shown in this figure, the g, capital G, is the center of gravity. And it acts on the weighting machine which offers resistance R. So the weighting machine reads a reaction R, and which is the force experienced by the man. So R is the apparent weight of the man. If we already discussed the action and reactional force, so if only mg is there, then we go inside the earth's surface, but it will not happening, because in opposite direction the normal force is also acting on the man or on it, and that is nothing but that is a reaction force R. That is a reaction force R, which is balanced by mg. Not balanced or not totally equal to each other, but it will be balanced mg. So, and this R is the, because of the so the net force acting on an object, that is, if R is greater than mg, then R minus mg. If mg greater than R, then mg minus R. That is also different depending upon the different position, different condition of the lift. So the net force that will be the that is acting on an object, that is the subtraction of this two, mg and R. Now for in first case, when lift move upward with acceleration a, when the lift will move upward direction. So normally from this figure, from first figure, you see that acceleration is upward direction, reactional force also be upward direction. So which force will be greater? That is the upward directional force. So R is greater than the mg. R is greater than the mg. So the apparent or the net upward force on the man, that will be R minus mg, that is equals to m into a, force into mass into acceleration of total of that lift, that is equals to R minus mg. So the apparent weight R equals to m into g plus a. So when a lift accelerates upward direction, the apparent weight of the man inside it increases. When the lift move upward direction, the apparent weight of the man will be increases. Now if the lift moves downward with the acceleration a, so normally the apparent weight of the man inside the lift will be decreases, and in this case the mg will be greater than the reactional force. So mg minus R, that is equals to ma, so R equals to m of g minus a. So the reactional force will be the apparent weight of the man inside the lift will be decrease. If the lift will move upward direction, apparent weight on the man is increases. If it will move downward direction, apparent weight on a man, that is decreases. Now when the lift is at rest or moving with a uniform velocity v downward or upward. So as this figure, this one, so acceleration is 0. If it is continuously at z, then also be it will acceleration is 0. And if it will moving with a uniform velocity v, either downward or upward direction, so if velocity does not changes, then how can we get the acceleration? We know that acceleration means velocity, rate of change of velocity. So we can say that the acceleration a equals to 0. So the force on a man, that is equals to r minus mg, that is equals to 0. M into a is 0, so r equals to mg. If you consider it will be upward direction, if you consider if it will be downward direction, then also you get r equals to mg. And from that two equation, the above two equation you placed in place of a 0, so you get r equals to mg. So in this case, the apparent weight of a man, that is equals to its actual weight when the lift is at rest or moving with a uniform or constant velocity v, either it will be downward direction or the upward direction. And last case is the when the lift falls freely. When the lift falls freely. So suppose the cable of that lift breaks, so the lift falls freely under the gravity. So in that time, the acceleration of the lift and the gravitation, that will be equal to each other. So the net downward force on the man, that is equals to 0, because a equals to z. So in downward direction, in second number equation, if you put either g in place of g, it will be a, or in place of a, it will be g, you get the net downward force acting on a man, that will be 0. So thus the apparent weight of the man becomes 0. This is because both the man and the lift are moving downward with the same acceleration g, acceleration due to gravity. So there are no forces of action and reaction between the man and the lift. Hence a person develops a feeling of weightlessness when he falls freely under the gravity. Weightlessness. In that condition, in fourth condition, when the acceleration of man and the lift will be equal to each other or the same, they will the person will feel there's no weight, weightlessness when he falls freely under the gravity. This is 1 marks question. Under which condition the person feels weightlessness? When he falls freely under the gravity. Clear? Okay, so this all about the impulse, some application. Also you can say that this will be the application of third law, action force, reaction force, balanced force, the conservation of linear momentum. Next class we discuss some numericals about all this, whatever the formula we studied in laws of motion, all related to all that formulas. And after that we started the friction, another one topic of this chapter, that is friction. So have a nice day. If you have any problem, then please inform in a comment box. Thank you very much.